Hi everyone, this is the first video for the course Calculus 2. I want to start by looking at the application you see on the screen. We've got a table for a function f of x. These are the only values of the function that we know. This represents you driving away from your house or from your home. X represents the time in hours after 12 o'clock noon, and f of x represents your speed or velocity at that time. We're going to answer or try to answer, or estimate answers to three questions related to this scenario, and I want to put the three questions up and actually answer them in reverse order. But when we're working these problems, I want to assume two things that don't really matter a whole lot, but just to make things simple. One is that let's assume we're driving on a flat, straight road, and then let's assuming that we're driving in one direction the entire time. So we're not worried about turning around or anything like that. That's some technicality we won't go into a lot of detail on, but let's assume those two things for now. So let's look at these three questions. So the first question is, how far away were you at 9 p.m.? And the second question is, how far did you drive oops, make that a little bit neater. How far did you drive from noon to 9 p.m.? Okay, and we'll put the third question up in a minute. But before we get to answering any of these questions specifically, I want you to think about first those two questions. And I want to know first, are those the same question as each other? Or is it possible those have two different answers? So maybe pause the video, think about that closely for a couple seconds, a couple minutes. And I want you to determine whether those two are two different ways to ask the same thing, or whether they're actually two different questions. Okay, so the answer to that question is that these could be the same thing, but they don't have to be. It depends on where you were at noon. And so let's say that at noon, you were already 150 miles away. Okay, if that's the case, then these two answers are closely related to each other. But let's say the answer to the second question, how far did you drive from noon to 9 p.m.? Let's say, I'm making this up, but let's say it's 500 miles. If that's the case, then if you drove 500 miles from noon to 9, then you were 650 miles away at 9 p.m. So the answer to number one would be 650 if the answer to number two is 150. And again, we're making the assumption you're driving in one direction, you're driving further and further away from home. So these are closely related to each other. Once we can answer one of the two questions, then we can immediately answer the other question. Both of these questions are pretty complicated from the data that's given. So given that we only have these 5 points on the function f of x, it's difficult to answer these questions. It's impossible to answer them exactly, but it's difficult to get a good answer. I want to look at a quicker version or a smaller version of question 2. And so question 3 is going to be, how far did you drive from 6 p.m. to 9 p.m.? Okay, and so I want to take a minute and talk about this, ways that we could approximate this. One thing to note is that the only relevant part of the table for this question, when we're talking about 6 p.m. to 9 p.m., the only relevant part would be the part between 6 and 9, and so 6 comma 99 and then 9 comma 62. Those would be the only two relevant points. And so the problem here is that the times are given, and f of x represents the velocity, not your distance. So you can't just subtract those. You can't do anything quickly to get that. There are several ways to make an approximation. There are two kind of simplest approaches to this. And so if we think about the graph of the function f of x, so when we look at the graph between 6 and 9 p.m., this is obviously not to scale, but let's say this is 6 and this is 9. We're on the x-axis here. And then we know that at 6, you were driving 99 miles per hour, and at 9, you were driving 62 miles per hour. So we know that the y value there is 62, the y value there is 99. Again, those are your speeds or velocities, not your distance. The issue is we don't know anything about what the graph looks like between there. So there are two simple assumptions that we can make. One assumption is that at 6 p.m., and a little bit before 6 p.m., let's say, you had it on cruise control at 99 miles per hour. And you kept your car on cruise control for 3 hours, going 99, way too fast, you're going 99 miles per hour. And then right at 9 o'clock, you see a cop and you're like, oh shoot, and you slam on the brakes and you start going 62 miles per hour at 9 o'clock. Okay, so say that again. At a little before 6 o'clock, you have it on cruise control at 99 miles per hour. You keep it at 99 miles per hour for those entire 3 hours. And then when you're right at 9 o'clock, you see a cop, you slam on the brakes, and you start going 62 miles per hour. In that case, for those 3 hours, you were really driving 99 miles per hour the whole time, which means that the distance that you drove is 99 times 3. Okay, so 99 miles per hour for 3 hours. That means you drove 297 miles. Again, that's an approximation. That's if we assume that we're correct about having it on cruise control. There's nothing about this problem to indicate that that's the case, but that's one way to think about it. Maybe we drove around 297 miles. Let's assume for a minute that we're correct that we drove 297 miles for those 3 hours. If that's the case, I want you to look at the picture and think what the graph would look like. So if you had it on cruise control for those 3 hours at 99 miles per hour, what would the graph look like? Would it be a line, a circle, a parabola, or something else? And so what it would look like, it would be a straight line, but it would be completely flat. And so we said that you had it on cruise control a little before 6 p.m. at 99 miles per hour. You kept it on cruise control at 99 miles per hour for those 3 hours. And then right at 9 o'clock, you slam on the brakes and you start going 62 miles per hour a little bit after 9 o'clock. And so the graph would be perfectly flat between 6 p.m. and 9 p.m. Okay, so I want to look at where this calculation would show up on the graph. And so I want to talk about a few things related to that. So in this case, we're talking about the distance that you drove from 6 p.m. to 9 p.m. And so I want to look at, for instance, like f of 6. So let's think about what f of 6 would be in this scenario. So f of 6 would be 99. That would be represented as miles per hour. So the units on that would be miles per hour. And graphically, that is the y value at x equals 6. Okay, and so the units are miles per hour. The graphical representation for f of 6 is the y value at 6. I want you to think for a minute, okay, is that always the case? So when we're finding f of 6, are the units always miles per hour? And on the graph, is f of 6 always the y value at 6? Okay, so the units are not always miles per hour. That's specific to this problem because it's telling you that velocity is miles per hour up on the top left of the screen. If you're graphing the function f of x, f of 6 is always the y value at 6. So graphically, it is always the y value at 6. The units are not always miles per hour. Okay, so the question is, where does the 297 come from? Or where does that show up on the graph? And so one thing that we might think about given that we've studied calculus for a semester up till now, is that we might be looking at the derivative. So if you looked at the derivative f prime of 6, if we're right about the graph on the left, so if you had it on cruise control a little before 6 and you kept it on cruise control until 9, then f prime of 6 is 0 because the slope there is 0. It's a perfectly flat line. Okay, so we should remember from Calc 1 that if you're taking the derivative at 6, you're talking about the slope at 6. Again, that's always the case if you're looking at the graph of f of x. If you're looking at the graph of f of x, the derivative at 6 is always the slope of the graph at 6. In this case, obviously 0 is not the distance that you drove. What it turns out that it is the units are miles per hour squared, which means this is the acceleration. In general, the way the units for the derivative work are the units for f of x are the units obviously of y, that has to be told to you in the problem. The units of the derivative are y divided by x. Again, that's a little bit informal, but it's the units of y divided by the units of x, and that goes back to the limit definition of derivative. If you remember from Calc 1, we have the limit as delta x or h approaches 0 of f of x plus delta x, or maybe you've seen f of x plus h, minus f of x all over x plus delta x, or x plus h minus x. Now obviously the bottom simplifies to delta x or simplifies to h, but if you look at the derivative meaning definition, which is written in red above the part where I've written units, that's how we calculate derivative. The things on the top, f of x plus delta x and f of x, those are both y values. The things on the bottom are both x values, so the units are y divided by x. That means that we always are calculating the slope. The units are always the units of y divided by the units of x when we're talking about f prime. The units are not always miles per hour squared. That's specific to this application. Okay, but the question still remains, where does the 297 miles show up on the graph? And it turns out that it's the area on that graph. So if you look at the area under the graph from 6 to 9, the area of that rectangle is 297. And so I want to talk about why. So first of all, obviously the area is 297 because area is base times height. And the height is 99 and the base is 3, and so obviously the area of that is 297. It's weird that area can be miles. Normally area would be something like square feet or square inches, or usually square units. In this case though, on the x-axis we're graphing hours. So the units here are hours, and the units on the y-axis are miles per hour, which means that the height is measured in miles per hour, not a unit that's normally associated with length. The base is measured in hours, again, not a unit that's typically associated with length. And so when we do this calculation, we're doing 99 miles per hour times 3 hours. The hours cancel and you get miles. And so the area there is represented graphically. The area of that is 99 times 3, or 297 miles. Now, you may remember from Calc 1 what symbol we associate with area. The area under the graph, and it's a little more complicated than that, but the area under the graph from 6 to 9 would be the integral from 6 to 9 of f of x dx. And we're approximating that as 297. It would be exactly 297 if this graph were correct on the left. The units there are miles. The units are not always miles. The units are miles here because it's the unit of x times y. It's base times height. And so the units in general for the integral are whatever the units of y are times whatever the units of x are. In this case, the units of y are miles per hour, the units of x are hours, and so we get miles for the units. Graphically, it's the area under the curve. So it's the area under f of x from 6 to 9. That's a loose term. I'm putting quotation marks around under because if you remember in Calc 1, you should have talked about things like net area and the total accumulation. It's a little more technical than just the area under the curve, but we think of it as being the area under the curve. And in this case, when we've got a function where f of x is all positive, it is the area under the curve from 6 to 9. And so graphically, the integral from 6 to 9 is always the area under the graph from 6 to 9, or the net area technically. It is not always that it's miles, but the units are always y times x. If we think back to Calc 1, the calculation we're doing here is called a left-hand sum. The reason we call it left-hand is because we kept the y value at the left endpoint. So we used the left endpoint 6 comma 99. We use that height 99 as the height for the entire interval from 6 to 9. It's called a sum because if you had more than one interval, so if we were doing from 6 to 9 and 9 to 12, we would use a new y value for the next interval, and we would then add them up. That's what we would do on problem 2. So if you go back and look at problem 2, how far did you drive from noon to 9? What we would want to calculate is the integral from 0 to 9 of f of x dx. The left-hand sum, so is approximately equal to the left-hand sum, which is then equal to the left-hand sum. So the height from 0 to 3 would be 43. And you drove for 3 hours, or the base of the rectangle is 3 hours. From 3 to 6, it would be 78 times 3. From 6 to 9, it would be 99 times 3. We can add that up quickly on a calculator or by hand, I guess, if we really want. And if we do that, we get 660 miles. In Calc 1, you may have gone over other approximation methods like using a right-hand sum. That's very, very simple. You might take the average of the left-hand sum and the right-hand sum. You might use a trapezoid or something like that. This is one method of approximation. It's not the point in Calc 2 is not how to approximate this. This is just something we're trying to review because we want to get at a better way to calculate this if we have more information than the 5 points on the table. Okay, so if we use the left-hand sum, our approximation for number 2 is 660. On number 1, that we said that were already 150 miles away. So the answer here is going to be 150 plus the integral from 0 to 9 of f of x dx, which is about 150 plus 660, which is 810 miles. All right, and so we would approximate by saying 810 miles. For sure, this is not accurate. The times between noon and 3, between 3 and 6, and so on, we don't know anything about them. This is just one way to approximate. It's very important to know from Calc 1 this stuff that we've got on the bottom right-hand corner of the screen. So the fact that f of x is the y value, f prime of x is y divided by x, which is the slope. The integral from 6 to 9 or from a to b of f of x dx, the units are y times x, and it's the area or the net area between f of x and the x-axis from a to b or from 6 to 9. In Calculus 1, you learned how to approximate things like this much more accurately, and given a formula, you found a way to do this exactly. You can use Riemann sums, which is what the left-hand sum and right-hand sum are called, and you can do the limit of the Riemann sum as the number of rectangles approaches infinity, or as the width delta x of the rectangles approaches 0, and get an exact answer. In Calc 1, you should have worked through those problems. They tend to be very tedious and difficult and sometimes nearly impossible to calculate using that method. And so you learn about antiderivatives, which is a better way or a more accurate way to approximate when it's possible to find antiderivatives. In the next video, we'll talk about the basic idea of the fundamental theorem of calculus, which is why we'd want to find an antiderivative in the first place. That's it for this video. Thanks for watching.